fault tolerance, fast and slow, exploiting failure asynchrony in distributed systems. My name is Jinlin Liu. First, let's talk about what is distributed systems. It is a system whose components are located on different network computers, and they communicate and coordinate with each other for the common goal, such as processing of same big problem, and that means we need data replication. The same data we need to store on multiple storage devices. And just like networks, this system also needs replication protocols. That is foundation nowadays upon with data center systems, is widely used in many cloud computing system. For example, the wheel-stamped replications. Here is a question now. Now we have the distributed system, but how could we ensure data security if any failure happens? And the answer is obvious that we need to store system state or need a backup of the data. Nowadays we already have two different ways of replication. The first one we call this disk durable mode. That means every node in this system is to synchronously persist updates to its own disks. In this way, when any failure happens, it can recover the data from its own disk immediately. That makes it very safe, but as we know, we need time to flush the data into the disks. That makes this form, the performance of this form is quite bad. But other contrasting method, which is called memory durable, it only buffs the updates in the memory of these nodes, and also obviously it is performant, but it will be at high risk for data loss and unavailability. So here comes the idea: why shouldn't us just combine these two words of replication together to be a hybrid protocol? So here comes their solutions. Situation where updates and crash recovery, the SAUCR. And the result of this protocol is quite inspiring, as all is always in 9% of memory durable systems with very strong reliability. And the basic ideas of SAUCR is also simple. It combines the two modes together and switched between each other, depending on different situations. When all the systems is healthy, that means all the many nodes is working well, and the system will work in fast mode, and they just need to buff it in the memory. It's the main cases, or common cases. But if failure happens, and the group found that only bare majority is up, it will switch to slow mode for guarantee the security of the data. Every node will flash data to disk. In this way, it can dynamically decide how to commit updates within three new technologies. First, we can see that it can situation-aware updates. Another is mode-aware recovery. To achieve these two approaches, they use LE maps. Now, but first we need to see how we already have, and then we could see that what they make changes here. First, we just briefly talk about these durable protocols. For the update scenarios, the client will firstly give the data to the leader, and the leader will commit the data to every of his followers. Then, every node in this group need to put the data to its own disks. And after this procedure ended, the leader has committed the update back up to the clients. So now we will face the condition about a scenario about recovery. Once the node crashes, it will directly, after it recovers, it will directly get the data back from its own disk. As it's very straightforward. But there is also another scenario that it got loading data as it has spent much time before it recovers. But it is also handled by this kind of protocols, because it can fetch the data with its reader. For the another mode, memory durable protocols, you can see the update procedure is quite similar. But this time the problem will be more simpler. Every node just need to buffer the data into the memory. But for the recovery, there are two different approaches. For the Oblivious, which means the system will do nothing when nodes fail. After nodes recover from a crash, it will directly lose the data and go back to work. In this way, we can see it cause data loss easily. For another method, which is called the loss-aware approach, it will realize loss and wait for majority when it's recovering. Until he gets a response, he will reload the data from other nodes. But however, this way is also faces some challenges. That is, sometimes this whole system will be unavailable. Here I will give some examples. For the Oblivious approach, there will be some data loss. For example, in this group, there is already 5 nodes of group. There are already 2 nodes that is filled. So if another node fails and recovered, we will lose data directly. And now, if another 2 nodes recovers, we will find that there are 3 nodes in this whole group have lost the latest committed update. That means the system has forgot the committed update, and that is data loss. For another example about the loss-aware recovery, it is within the same scenario, but this time the nodes will be recovering state. That means you wait for the response from other nodes, but until it gets the majority responses, you will he could do something. But this time, the majority of nodes in this group is already done. So when this nodes recovers, they cannot get the majority response, and none of them will do any actions. So the whole system will be shut down and permanently unavailable. That could be worse for some times. So the problem we can see that is the majority of the nodes lose data, just like what we see. The system will shut down because this majority of nodes has no backup of these disks, and he cannot believe that others have that data. So it will be the same problem for the fast mode in SAUCR. The SAUCR will know that we can switch between 2 different words, switch between memory durable and disk durable, which is slow mode and fast mode. However, we will meet that big problem that all the nodes fill at the same time. That means no gap between different filters, and we can have no time to gather the messages and do any actions. In this scenario, no time will we have to switch between 2 modes, and the SAUCR will also be unavailable. But unfortunately, these cases are quite rare. In contrast, the time gap between these correlated crashes, that is maybe caused by raspberry power time outage, for etc., could possibly exist, and the possibility that the gap is longer than 15 ms is 99%. That is very big number, and now we can conjecture that the gap between filters always exists. That will be the precondition of following discussions. Now we can talk about the SAUCR, how it works. First, we already see that this situation where updates that switch from different modes. For another scenario, that is crash recovery. Thus, every node, when it's recovering, needs to know its pre-crash mode. When you know that he has crashed in the slow mode, that means it has backup in his disk, and you will directly get the data back from its own disk. That will be straightforward. For another scenario, when it crashed in fast mode, that means it has lost all the data and have no backup. He had to get the data back from other nodes. He also will wait for the majority responses, just like the memory durable protocols. And to achieve these two approaches, they use replicated latest lottery entry, which is called LE map, to help nodes recover which mode they are before the crashes happen. So when a field happens, how do the SAUCR react? A basic mechanism, we say, the filter for the filter detection is called heartbeats. The leader will periodically check this follower is alive or not, and once the follower suspects that the leader has failed, they will compete to become the new leader and continue the work. That's the basic ideas. And now we add new properties. The leader will, once the leader suspects that only a bare majority, in this example, that only 3 nodes works, it will switch the whole system to slow mode, and every node will flash the data to its disk. For another scenario, once the leader fails, and we can see that other followers will compete. But first, we will directly switch to slow mode to guarantee for the safety of the data. So let's see the example of how SAUCR works for total procedure. First, we have a 5 nodes group, and only one in this node is crashed, and the majority of nodes is working well. Okay, it will still work in fast mode. But now, when 2 nodes in this 5 nodes group crash, the leader will find that they are in danger, and it will switch to slow mode, and everyone needs to flash the data to the disk. And everyone have a backup, and when the new nodes recovers, the two nodes recovers, it can directly get a backup from other nodes. And when any nodes has crashed in slow mode, it can directly recover because they have a backup in the disk. To achieve this approach, they use 2 different index pair, which is called fast switch entry and the latest on disk entry. We can see that the fast switch entry is created on the fast mode, and latest on disk entry is created in slow mode. And we can compare and see which one is the latest logged entry. I will see which is, and the nodes will see which mode it was before the crash. For example, if the latest on disk entry is upper than the fast one, it means the nodes crashed on the slow modes. And now everyone knows the latest logged entry, and we can build a LE map, including all the informations of any other nodes. But with the help of LE map, we can communicate and interact with other nodes more frequently. When one node is recovered from a crash, you will firstly send LE query to any other nodes and see which the updates is working now. And then, after it constructs the LE map, it will reload the data. It is the true mechanism of how the SAUCR works. And in this mechanism, we can guarantee that all comment sheet updates is saved in this system. Now let's make some reliability testing. First, they created a cluster crashing testing framework that make a sequence of events like crash or recovery become a sequence, and they can test the system continuously. For example, is this event chain, the 5 nodes will crash at first, and then the 4 first nodes crashed, or the etc. In this way, they get the result after thousands of testing, and they see that the SAUCR works very well. It provides a high, at most the even high reliability, just as the same as the disk durable ones. Compared with memory durable protocols, each one is faced high risk of data loss, and another one faces high risk of unavailability. The SAUCR works quite stable, within a few missed unavailable cases, but it's less than 10%. So in another testing, for the performance testing, you can see that SAUCR works almost the same as the memory durable ones, and it will be much faster than the disk durable one. Now we can say that the SAUCR provides both high performance and reliability. Make a summary here that the replication protocols are very important, and they need two properties. One is performance and another high reliability. But the existing protocols nowadays cannot provide both of them, but SAUCR could do it. That's quite good. Great. Okay, that's all.